Hello, welcome to this video. We're going to talk about work, energy and power today, and this should hopefully be useful, more in-depth information about these three ideas, and we'll do also some examples in later videos on a few questions, so you can get a better idea of how to use these ideas in order to solve problems. That's really the use that these ideas have, the work, energy and power idea. They all have associated formulas where you can calculate each of these three, and they are also very much related, and they're just kind of ways of looking at problems. So instead of, for example, working out questions using the usual V equals U plus AT equations and the S and all of those, and finding aspects of the velocity, the acceleration and the time for the movement of things, sometimes it's much easier to use the ideas to do with conservation of energy or work done or power per unit, or just the power transferred, and these kinds of ideas in order to solve problems. So with time we'll develop a nice intuition as to when to use which idea. Apologize for the barking dog in the background. And so let's go with the definition of, or one of the ideas that it's useful to think about in terms of when we think about energy and we want to know what energy is. So the most useful or practical one that I've found so far, in terms of the course that you're all doing, is this one. It says that the energy is really the capacity to do work, and we will look at what work is also a bit later. And so to think about energy in this way is useful. So if there is energy located somewhere, then there is capacity to do work. For example, if there is excuse me, if there is water up here somewhere on a kind of slope or a cliff of some kind, and then the water falls down this way due to gravity, then the potential energy that the water has when it's up here, which is normally expressed as gravitational potential energy, and is a function of the mass and the amount of mass of water that there is there. That's how much work the water can do when it falls down. The energy transforms into kinetic energy here in the movement, and then if we put some cleverly arranged kind of generator, I don't know why it's green, generator here, then this can turn around due to the water that is falling, and its own energy is then transferred into the kinetic energy of this rotating generator, and that can then produce electricity. So this stored energy up here is then capacity for it to do work, and work is really defined as the force done applied over a certain amount of distance, and its units is joules. It's a type of energy, but we'll talk about that in a bit more detail a bit later. I just wanted to give you a sense for what the idea behind this definition is. So let's delete some of this and talk about the three types of energy that we're going to be dealing with in this course, really the main ones. So the first type of energy is kinetic energy. Kinetic energy is the energy that a body has due to the motion that it has, and this is important when the particle is moving at low speeds, the low speeds compared with the velocity of light. So this is really the energy of a body due to the motion at low speeds. This is low speeds with respect to velocity of light, which is normally we call c. And the formula for kinetic energy is 1/2 m, so 1/2 times mass times velocity squared. So remember that only the velocity is squared. The mass is just normal, and we only square the velocity, so be careful with that. So then another way of saying this would be 1/2 mv squared, okay, and not mv squared. That's different. That would be m squared v squared, okay, and that's not the formula. The formula only the squared only refers to the v. Okay, so then we can frame this in a little nice color and try to remember this because it's very important. Okay, next would be the base units. We'd have to talk about the base units of the kinetic energy, and it's important to know that the base units, if you can express them first in terms of the formula. So if the units are, so let's talk about the base units. We have kinetic energy is equal to 1/2 mv squared. So in terms of units, this is joules, which is kinetic energy is expressed in joules, and on the right hand side we have kilograms. The half doesn't have a unit, it's just a number. We have kilograms, then meters per second, which is the velocity, meters per second squared, right? And this should say kilograms for mass. And so that turns into kilogram meters squared, kilogram meters squared. Then s to the minus 1 squared is s to the minus 2, and that's joules. So that, in other words, a joule is the same thing as a kilogram meter squared per second squared. Okay, so those are the base units. When you think about joules and you want to know what the real sort of base units of joules are, you can think about it like this. You can calculate it like that, and that's kilograms times meter squared and then divided by seconds squared. That's the unit of energy. So these are the base units of kinetic energy. Now let's talk about the next type of energy that we're going to encounter in this course a lot, and that is gravitational potential energy. So gravitational potential energy. We've underlined one, let's do the same thing to the other. Now, gravitational potential energy can be thought of as it's the body's energy. So this is a body's that's not properly spelled. Body's energy due to the changes in its gravitational energy. So due to changes in its gravitational energy. And this is normally seen as a calculation. The one we're going to use is normally used for distances close to the Earth's surface. So a body is changing height, really. So the body's energy due to changes in its height is another way of saying it. And this is normally defined as gravitational potential energy equals the mass times the gravitational pull or gravitational constant, which we normally use, gravitational pull times the height. And this is normally the change in height. Change in height, so that's m times g times h. That's the gravitational potential energy. And what that means, or the way that we calculate that, is very simple. It's one of the easiest things to calculate in physics, really, and that's why it's so useful in many problems. Imagine you had a cliff like this, and here at the top you had some guy, and they ask you in a question, what is the difference in his gravitational potential energy when this height is 100 meters? Then what's the difference between him when he's up here or him when he is standing here? So the difference in his energy between there and there would be his mass. So you'd have to know his mass. Let's say it's 80 kilograms. His mass, so the gravitational potential energy that he has up here compared with here, it's always a relative thing of comparison between two heights, would be equal to his mass times his gravitational pull, which is always 9.8. So I will put it in brackets. Times 9.8 times the height difference. The height difference is 100 meters. So if you calculated this, you would get 78,400. Just did it on my calculator. Joules, right? 78,400 joules. And the meaning of that really is, how would that be useful? For example, if they ask you if he jumps and he just free falls down, then if they ask you how fast is he going when he's at this height, maybe he's about to hit the floor or just about to open his parachute or whatever, and they ask you how fast he's going there, you can either use the normal v equals u plus at equations and all of that, or you can just say, well, this is the amount of energy that he's gonna lose in terms of gravitational potential energy, because here he's at a higher at a larger height than here. He's gonna have more gravitational potential here than there, so that's the amount of energy he's gonna lose. So all of that energy, if there's no air resistance, and normally in the question they will tell you, it will go into kinetic energy. That's a conservation of energy principle, which we'll talk about in a bit, where no energy is lost but only transferred or converted. In this case it's converted into kinetic energy, and from up here we know that the formula for kinetic energy is half mv squared. So then we know that the half mv squared will be equal to the amount of energy that he gets from his fall. So then we can solve this and say, well, that would be, if I pass the half to the other side, it becomes a 2 on the top. So that would be 2 times 78,400 divided by the mass, because it's here multiplying, so it comes on the other side dividing. Then I do the square root of that and I get my velocity. So I won't do that now, but that would be a really easy way of calculating the velocity when he's here at this height. Hopefully that makes sense. And similarly you can do the opposite. You can say, well, I'm going to throw a ball, and this ball I'm going to throw it up, and it's got a velocity of 20 meters per second when I first let it go, and please tell me what height it reaches. Well, then you can use also a half mv squared, and that's going to equal the potential energy it's going to get at the top, so mgh. So from here you can, v, well, they would have to tell you m, maybe it's 1/2 kilo, half a kilogram, pretty heavy ball, and so then you know the mass and the velocity, and you know g, and therefore you would know the height. If there's no air resistance, again, if there's no air resistance, then actually the mass is even cancelled, so the mass doesn't really matter of the object, which is a bit counterintuitive, but we can talk about that in another video in a little bit more detail. So hopefully that gives you a sense of what we normally use gravitational potential for. And let me just delete some of this stuff, since it's shouldn't be part of the notes necessarily. It's part of okie doke. So we're running out of time pretty much, so in the next video we'll talk a little bit about the third type of energy that we use in this course, that we discuss, and that's elastic potential energy. Until then, take care.